Good day, everyone. All right, seniors. Now, let's quickly finish the exercise we were treating on elasticity and expansion and the rest. We last question we did was number 26, so let's do numbers 27 to 30 now. In number 27, the question says the force extension graph or the force extension curve of an elastic rubber is shown in the diagram below. This is the diagram right here I have drawn. It's shown in the diagram below. This is the diagram. The question says the force extension graph of an elastic rubber is as shown in the diagram below. Calculate the work done between E and F. Okay, like we have done before, look at this question very well. What it means to find the work done here. So did they call it work done or energy? Let me check. It says, okay, the energy stored when the wire is stretched from E to F is, okay, they didn't call it energy stored, but they didn't call it work done. They called it energy stored, but it's the same thing. The work done is stored as elastic potential energy inside the rubber or inside the wire. So we simply use energy or work. Work done or energy stored, we said before, is average force of extension times the extension produced. So the work done is what? Half Fe. That means that in this question, we don't seem to have a particular value for F or a particular one for E. There seems to be a range. So what we should just do here as students of maths is to change, what we will just do is to change our F to half delta F times delta E, and change our E also to delta E. So instead of F, we write delta F. That means average change in force applied times change in distance. It means the same thing, because here the reason we are using delta or change is that we are going to find the extension as a difference between E and F. Also, at E, when the extension is 0.05 or when the length is 0.05, the force is 0.1. At F also, when the length is 0.10, the force is 0.20. So you will see that here too, there's a delta F. There's a change in F. And in this range, there's a delta E. So that makes sense now. We are going to do work done is 1/2 times delta F times delta E. Let's go ahead and sort out the values. 1/2 times F2 minus F1. Delta F will be final force minus initial force. That's the force at F minus the force at E. Okay? Then delta E will be what? Delta E will be what? E2 minus E1. That's the extension or the length at F minus the length at E. So at the end of the day, it still gives us the same answer. So we are going to do energy stored is half times what? 0.2 minus 0.1, half times 0.2 minus 0.1, half times 0.2 Newton minus 0.1 Newton times 0.1, is it centimeters or what? Okay, times E2 minus E1. That's 0.10 meter minus 0.10 meters minus 0.05 meters. So that minus 0.05 meters. That we, answer our question. Let me write my overlay so it doesn't look like something else. So your work done or energy stored is half times 0.2 minus 0.1. That's 0.1 newtons. Then 0. Also 0.10 minus 0.05 is going to be 0.05 meters. You can press your calculator to check that. So that gives you 0.05 newton times 0.05 meters. That gives you 0.05 newtons times 0.05 meters. That's 5 times 10 raised power minus 2 times 5 times 10 raised power minus 2. So 5 times 5, what's it? Times 10 raised power minus 2 plus minus 2. I hope you get what I'm saying. That gives you what? 25 times 10 raised power minus 2 plus minus 2 will give you minus 2 minus 2. Plus times minus there. You know this is plus times minus. The bracket means multiplication. So minus 2 will give me minus 4. So my work done is 2.5 times 10 raised power 1. 25 is 2.5 times 10 raised power 1. So that's 2.5 times 10 raised power 1 times 10 raised power minus 4, which gives 2.5 times 10 raised power 1 plus minus 4. So if you do your math well, you get 2.5 times 10 raised power 1 minus 4. 1 plus minus 4 is the same thing as 1 minus 4. So that helps us get our energy stored in the wire as 2.5 times 10 raised power minus 3 joules. See, instead of all of this, I could have done it straight. I could have said, okay, work done is energy stored. Energy stored in the wire is work done, which is half Fe. So my extension is L2 minus L1, which is 0.10 meters minus 0.05 meters. And that gives me what? My extension as 0.05 meters. Also, I would just say my force applied is what? Final force minus initial force. That's 0.2 newtons minus 0.1 newtons, which is 0.1 newtons. So I know my force now and I know my extension. So I just go straight and do energy stored is work done. Energy stored in the wire is work done in extending it, which is average force times extension. And that gives me what? That gives me energy stored as 1/2 times 0.1 newton times 0.05 meters. And that will be what? That will be 2.5. I just pressed my calculator. 2.5 times 10 raised power minus 3 will be equal to 0.0025 newton meters. 0.0025 newton meters, which is 2.5 times 10 raised power minus 3 joules. I could have just gone straight like that, but sometimes, because I intend to show you some indices in addition, I went this way and did the indices all together. So just in case you are, you could do this with your calculator. Get the extension, you understand? Get the extension, get the force, multiply with your calculator, half times 0.1 times 0.05, get your answer straight, change it to standard form. You could go that way, but sometimes when you don't have a calculator in some kind of tests or exams, you need to do it step by step like this. So that will help. All right, that's question 27. 28 now. Question 28 now. Question 28 says if a load of mass 10 newtons stretches a cord by 1.2 centimeters if a load of mass 10 newtons. So the force applied by the load is 10 newtons. Stretches a cord by 1.2 centimeters. Am I right? Okay, correct. Stretches a cord by 1.2 centimeters. What is the total work done? What is the total work done? Okay, this is a simple question. First thing we need to do is change our extension to SI unit. 1.2 over 100 will give 0.0012 meters. So the total work done, okay, the total work done will be what? Half FE. The total work done. I want to try something here. So don't write now. Let me just try and check what the question means by total work done first. Using half FE. Half FE will be half times 10 newtons times 0.0012. Press your calculator and see what you get for this. Press your calculator and see what you get for this. This will give you 5 times what? 0.0012. That's what? 0.0060 Newton meters. 0.0060 Newton meters is the same thing as 6.0 times 10 raised to the power minus 3 Newton meters, which is the same thing as 6.0 times 10 raised to the power minus 3 joules. Okay, let me write my J well there. So that's the total work done. That is the total work done in stretching the string. I'll just check. Okay, 6.0 times 10 raised to the power minus 2. Is that correct? Let me check. Is there any mistake? Oh, there's a mistake here. I overshot these decimals. So it should be 0.0. It should be 0.012 meters. So let's correct our mistake. It should be 0.012 meters. So 0.012, and that gives what? 0.06. That gives me 0.060 Newton meters, which is 6.02 times 10 raised to the power, which is 6.0 times 10 raised to the power minus 2. 6.0 times 10 raised to the power minus 2 joules. Okay, that's correct. I initially thought that total work will mean something different, but it just simply means the same as the work done in stretching the cord. Okay, let's go to question 29. The diagram below represents the graph of the force applied in a stretch. The diagram below represents the graph of the force applied in stretching a spiral against the corresponding extension. The force constant of the spring is, all we need to find in this diagram is, find a force and its corresponding extension. You understand? Find a force on the graph and the extension it produces. If you look at this graph very well, the 120 Newton force, this vertical axis is for force and the horizontal axis is for what? Extension. Sometimes extension is written as x. So notice that if you look at the graph from the 120 Newton, trace it from 120 Newton to the right and trace it down, you will notice that the 120 Newton force produces an extension of 6 meters. Okay, are they in SI unit? We are not sure. Okay, let's just assume force and extension. Okay, the question is not very written properly there. Okay, what number? 29. I'll just go ahead and draw let me draw. That would be much more better for us in explaining. Okay, so we are going to correct what we said we don't like in the graph. Extension is in meters. Force is in what? Newtons. It is good practice to keep your SI unit where they should be. All right. So it shows that the graph goes straight like this, an extension, and okay, let me just okay, I think we are getting close. Just wanted to look neat there. All right. Okay, notice that when the force of extension is 120 newtons, the what? The extension produced, when the force applied is 120 newtons on this axis. When the force applied is 120 newtons on this axis, on the force axis, the extension produced is what? 6 meters on the extension axis. So let's just fill the rest. 0, 20, 40. Okay, I think I'm overshooting that. 0, 20, 40, 60, 80. Pay attention, please. 100, 80, 100, then 120. Then this is 0, 1, 2, 3, 4, 5, then 6. Okay, I think we should put it to make it look complete. Okay, all other forces have their own corresponding extension that which they produced, but we are okay with just picking these two. A force of 120 newtons. The graph shows that a force of 120 newtons produces an extension of what? Of 6 meters. So that will get us our force constant. Using F is equal to KE. That's the relationship between force and extension in an elastic material. F is 120 newton. The extension is 6 meters. The extension produced is 6 meters when a force of 120 newtons was applied, according to the information on the graph. So that means substituting 120 is K times 6. That gives you what? 6K. That gives you 6K is 120. And that's K is 120 over 6. That gives you what? K is 120 over 6. So K is what? 20. 120 is in Newton, don't forget. 6 is in meters. So K is 120 newtons per meter. We can also write it like this. So the force constant of the spring is 20 newtons per meter, not 120. The force constant of the spring is 20 newtons per meter. Let's go ahead and do the last question in the exercise. It says the work done in extending a spring by 40 millimeters is 1.52 joules. Calculate the elastic constant of the spring. Okay, 40 millimeters. Okay, that's a simple question. Okay, work done is 1.52 joules when the extension produced is 40 millimeters. The work done is 1.52 joules when the extension is 40 millimeters. So let's first of all change millimeters to the SI unit. That will give us what? 0.04 meters. So the extension produced when the work of 1.52 joules is done on an elastic spring the extension produced is 0.04 meters. So using what? Using work done is half ke squared. Using work done is half ke squared. What does this give us? It means 1.52 joules is half times k times what? 0.04 squared. Let's be, attentive, please, seniors. Okay. Elastic constant means the same thing as force constant. In an elastic material, elastic constant refers to the same thing as force constant. So this is k times 0.04 times 0.04. That's 0.04 squared all over 2. So what did we get? I think we can cross multiply. Or let's just divide 2 here 1, 2 here 0.02. So that gives you what? 1.52 is what? K times 0.02 times 0.04. So, okay, multiply. This is 2 times 4, 8. Okay, this is K. Okay, let me simplify so that you can understand it well. 0.02 is 2 over 100. 0.04 is 4 over 100. So I would have written this as 8k over what? Over 10,000 is equal to 1.52. I'm just assuming you don't need to use your calculator as much as possible. So this is 0.8 over 10,000 is 0.000 then 8. You understand? The 8 over 1,000, the 8 over 10,000 will give you 0.008, and if you multiply it by k, it becomes 0.008k. So let's remove the 1 here. We don't need it. Let's just make our left hand side be 1.52. So rearranging 0.0008k is what? 1.52. So k is 1.52 over 0.0008. So k is equal to what? You get your answer in Newton per meter. You get your answer in Newton per meter. So that's the elastic constant of the spring. That brings us to the end of our examples of our sub examples on elasticity.